Okay, so let's take a look at bond energy on a larger scale. If we're talking about not just a few atoms, but many, many, many atoms. Let's say you're dealing with maybe, and this is still a pretty small sample, but let's say you've got 1,000 atoms. Typically, we'd be dealing with way more atoms than that. 1,000 atoms is a ludicrously small sample. But let's just use this as an example for now. If you got 1,000 atoms and they're just clustered together, let's say you put in one atom and then a couple other atoms close to it. So that would be equilibrium distance, R naught. Let's say we put in a few more atoms. Where could those other atoms cluster so they're all close to this central atom?
Up top.
Up top. If we put it directly above, that's equilibrium distance from this atom. But it's kind of far from this atom. That'd be a square root of 2 thing, not just one R naught. So how can we put this so it's closer to this atom, closer to this atom?
It'd be to the diagonal a little bit, right?
Yeah, if we just roll this a little bit to the side, we can put this atom close enough to both of these atoms. So these are all equilibrium distance apart. And that leaves room to put another atom here, equilibrium distance from these, and this one. And then we could put 2 more down here. So we're essentially establishing a hexagonal grid. You could keep putting in more atoms with each row being offset. And then just keep that pattern going for as many rows as you like. And this allows us to pack the atoms more closely together than a rectangular grid would with right angles. Because this way, each atom is immediately adjacent to 6 nearest neighbors. And if you draw in all the bonds here, you end up getting these hexagonal shapes. And so on. So this would be a hexagonal grid. A close packed arrangement. And of course, atoms don't have to be in this arrangement. You could have atoms arranged in other shapes as well. You could have atoms in maybe a square lattice. Maybe everything is right angles because of the structure of that type of atom. In that case, how many nearest neighbors would each particle have? Like this particle here, how many nearest neighbors does it have?
8.
Are these all equally distant?
No.
So we wouldn't call them all nearest neighbors. How many of them are at some closest distance?
4. Right.
There's 4 of them. Because these diagonals are slightly longer distances. That's square root of 2 R naught rather than just 1 R naught. So in this square arrangement, with everything at right angles, each particle has only 4 nearest neighbors because the diagonals are slightly further apart. So this is not as close packed as the hexagonal grid is, but this is another possibility. The idea of the crystal structure of the substance is all about how the atoms are arranged with respect to each other. So 6 is the maximum. You can't get them closer packed than this in 2 dimensions. But we don't live in a 2-dimensional universe. We live in a 3-dimensional universe. So if we're looking at some central atom here, let's say we're considering, let me clear some of this out. If we're considering this as the atom we care about for the moment, that's got 6 nearest neighbors in the same 2-dimensional level. But where could we put even more neighbors immediately adjacent to that? Could we fit another atom that's equilibrium distance from this one?
In front?
Yeah, if we go out in front. So because we live in a three-dimensional universe, so if we have an entire layer of hexagonal grid, we could put another layer of hexagonal grid in front of that, three-dimensional. And if you just stack it directly on top, you've got one nearest neighbor above and one nearest neighbor behind, or one nearest neighbor outside and one nearest neighbor inward. But we could actually do better than that. If we stack these grids out and offset, we could have one more atom here, sort of nestled into that crevice there. We couldn't really put one here because it would overlap, but we could put one in the next crevice. And then this would overlap too much, but we could put one here in the next crevice. So in addition to these 6 in the same layer, we would also have 3 in the next layer out, and also 3 behind, 3 in the next layer in. So this one atom, this one central atom would actually have 12 nearest neighbors. In 3 dimensions, an atom can have up to 12 nearest neighbors. 6 in the same layer, 3 directly in front, and 3 directly behind. So a close packed arrangement in 3D would lead to each atom having 12 nearest neighbors. So in 3 dimensions, that's the maximum possible. You might have fewer than 12 nearest neighbors if you've got some sort of crystal structure. For instance, in a 3D square structure, you'd have 4 nearest neighbors in the same sheet, 1 directly in front, 1 directly behind. So in a square grid, 3-dimensional, you'd have 6 nearest neighbors per particle. In a hexagonal 3-dimensional grid, you'd have 12 nearest neighbors per particle. And 12 is the most. You cannot pack them tighter than this in 3 dimensions. If you go to 4-dimensional universe, then you could pack more. There's entire branches of mathematics dealing with how closely can you pack spheres in n dimensions. But in 3 dimensions, 12 is the theoretical maximum. So 12 would be how many nearest neighbors per particle you can expect in this close packed arrangement. Any questions on that so far? And that's typically what you would expect if the particles are just smashed as close together as they can be with no sort of crystal structure inherent to that. So let's see how we would apply that to a large cluster of particles. Let's say we've got many, many particles. Let's say 1,000 is probably not even enough. Let's say we've got 1,000,000 particles, which is still on the small side. That's still microscopic. But let's say just 1,000,000 for convenience of the numbers. We've got 1,000,000 particles. Let's just say they're monatomic. We usually call that capital N, the number of particles. And how many, assuming it's close packed, we're assuming 12 bonds per particle. And how could we use that to figure out the total number of bonds involved here? If there's 12 bonds per atom and there's 1,000,000 atoms, how would we figure out how many bonds there are?
You'd be doing 12 over 2 times n?
Yeah, and why do we divide by 2 there?
Because you don't want to double count.
Right. If we just multiply 12 times 1,000,000, I mean, that would make sense in terms of units. We've got 12 bonds per atom. We multiply by 1,000,000 atoms. Just in terms of units, atoms and atoms would cancel out. But if we're counting those up one at a time, I'm just going to draw this 2-dimensionally for now. But if we're saying each atom has a certain number of bonds, like in 2 dimensions, we'd say each atom has 6 bonds. So this atom has 6 bonds. And then the next atom, this atom here has 6 bonds. 1, 2, 3, 4, 5, 6. And then we could say this atom has 6 bonds. 1, 2, 3, 4, 5, 6. And this atom has 6 bonds. 1, 2, 3, 4, 5, 6. In the process of doing this, if we just apply this 6 bonds per atom to every atom, we're counting every bond twice. We're counting the bond from A to B, and we're counting the bond from B to A. We don't want to count everything twice. So we have to divide the finished result by 2. We take our number of bonds per atom times number of atoms, but then divide that by 2 to eliminate double counting. And of course, you would only do that if your approach actually does count each bond twice. If you're dealing with some more complicated arrangement than just a bunch of atoms of the same type, you want to check in an actual diagram like this, say this atom has this many bonds, and actually draw them out. Then look at its neighbor and say this atom has this many bonds and draw them out. And if doing so marks each bond twice, then you have double counted and you need to divide by 2. In this case, that means we get 6 million bonds. So that's the number of bonds, or at least bonds of that type, the number of nearest neighbor bonds. And what do we call the energy in each one of those bonds?
Epsilon.
Yeah, or since it's bonded, we call that negative epsilon. So we've got 6 million nearest neighbor bonds at negative epsilon each. So we can just multiply those. Number of bonds we found times energy per bond. So E bond of those million atoms would be negative 6 million times epsilon. So that's how we would calculate the bond energy of that entire structure. And this is, of course, only looking at the nearest neighbor bonds. We could also look at the second nearest neighbor bonds by working out number of second nearest neighbor bonds per atom times a million atoms divided by 2 to eliminate double counting, and then multiply that by some fraction of negative epsilon, whatever the value of a single second nearest neighbor bond is. But that's going to be more complicated, and it doesn't really change the result by very much, because most of the energy comes from the nearest neighbor bonds. Second nearest neighbor bonds being further apart are weaker, so the nearest neighbor bonds gives you a pretty good approximation on its own. Any questions on that so far? One other thing to be careful about here, in this case, we're assuming that every atom has 12 bonds per atom. But in this million atom cluster, would there be any atoms that don't have the full 12 nearest neighbors per atom?
The edges, right?
Yeah, if we take a look at the edges, like even in this two-dimensional system, we're assuming that every atom in 2 dimensions has 6 bonds. But if we look at the edge, like this atom on the corner here only has 2 bonds. This atom has 1, 2, 3, 4 bonds. So the atoms on the edges are going to have fewer nearest neighbors per particle, and that's going to bring down the average. So that leads to an underestimate, or sorry, an overestimate, because we're assuming there's more bonds than there really are. So ignoring the edge effects is going to overestimate the amount of energy involved, but ignoring the second nearest neighbors and beyond is going to underestimate. So if we're lucky, maybe the overestimate and underestimate at least partially cancel out, and we'll get a pretty good approximation. If you want to be really accurate, then you would want to include the second nearest neighbors, maybe even the third nearest neighbors as well. The thing is, for edge effects, you only really need to worry about edge effects at all under what sort of circumstances?
Small number of atoms, right?
Yeah, if you got a small number of atoms, then most of them are going to be on the edge. Like if I draw out, let's say we look at 2 dimensions. If I just draw out a square that's like 3 by 3, of those 9 atoms, 8 of them are on the edge and only 1 of them is interior. So most of them are on the edge. If I instead draw a 4 by 4, we've got 16 atoms, of which 4 are interior and the other 12 are exterior. So they're still mostly exterior. If I make this 5 by 5 though, and let's say we make this even more extreme, maybe 6 by 6, 7 by 7, 8 by 8, 9 by 9, 10 by 10. The larger this gets, the more percentage of the atoms are in the interior. So if you've got a square that's like 1,000 by 1,000, almost all of them are in the interior and very few are on the edges. And typically we're not looking at 1 million atoms or 1 billion atoms or 1 trillion atoms. What's a typical number of atoms to expect in a sample, an everyday size sample?
100. 100.
100 is absolutely microscopic. That is an extremely small number in terms of atoms. I mean, if you're talking, it depends on what you're talking about, of course. Like 100 elephants is pretty big. 100 atoms is ludicrously small. But think back to chemistry. What do we usually?
A mole.
We usually don't describe like the number of molecules. We describe what?
Moles, right?
Number of moles, right? So 1,000,000 atoms is actually extremely small compared to a mole of atoms. One mole is actually how many particles?
6.02 to the 10 power 23.
Yeah, 6 times 10 to the 23rd atoms or molecules. In other words, a 6 followed by 23 zeros. So that is 1,000, million, billion, trillion, quadrillion, quintillion, 600 hextillion atoms. That is a colossally huge number of atoms. And this is just on an everyday scale of amount of atoms we'd be dealing with on a typical everyday basis. So 1 mole is such a colossally huge number of atoms that we can expect them to be almost all on the interior and almost none of them are on the edge. So in a typical size, like on the size of a mole, or even just like a 1/1,000,000th of a mole, you can assume that they're almost all on the interior. The edge effects round off to 0. Any questions on that so far? So we can use this to build a formula for bond energy. Looks like what we were doing here was we were taking 12 bonds per atom. That's just number of nearest neighbors per atom. So we take number of nearest neighbors per atom times number of atoms, capital N, divide by 2 to eliminate double counting. That'll tell you the number of particles, or sorry, number of bonds of that type. And then we'd have to multiply that by what?
Epsilon?
Yeah. Because that's the energy in one bond. We've got number of bonds times energy per bond. Also, since it's bonded, we want to treat this as negative. So we now have a formula for bond energy based on the microscopic behavior of the individual bonded atoms or bonded molecules. So we can use this as a formula for bond energy. Also, since we're usually not dealing with number of atoms so much as number of moles, we can also set up a conversion here. Avogadro's number is the conversion factor between moles and number of atoms. Number of moles, usually written as N. Like, let's say you have 5 moles. How would you convert 5 moles into a number of atoms?
5 times Avogadro.
You just take the number of moles, lowercase n, multiplied by Avogadro's number, 600 quintillion, or 600 hextillion, sorry, and that tells you the number of particles, capital N. Which means we can replace capital N with lowercase n times Avogadro's number. We can write E bond as negative number of neighbors per atom times number of moles times Avogadro's number divided by 2 times epsilon. So that is another formula we could use for bond energy. Any questions on that so far? And this means that if you wanted to break all the bonds, like let's say you want to go from a solid to a gas, you'd have to add this much energy as a positive. And that means the energy you'd have to add to break all the bonds depends only on the crystal structure, how many neighbors there are per atom, the size of the object, how many moles there are, and epsilon, the strength of each individual bond. In fact, we could even take this a step further by comparing it to the other formula we were using for bond energy from the very beginning. At the very start of the quarter, before we even got into molecules and stuff, What was the original formula we were using for bond energy?
Change of mass times, enthalpy of whatever.
Delta H value, a constant for that material. And I'm going to leave off the delta on the mass because we're looking for how much energy there is here, not just the change in energy. Strictly speaking, that also means there should be a negative sign here because the energy is below 0 if it's not bonded, or if it is bonded. However, here we're not looking at this in terms of mass. We're looking at it in terms of number of moles. So instead of using mass times enthalpy of melting, we could say bond energy is negative number of moles times the molar enthalpy of melting. So delta H mole is the energy per mole to break all the bonds. So this would be a macroscopic formula for bond energy. Macroscopic in the sense of looking at the big picture, external observations. Whereas this would be a microscopic formula for bond energy. Microscopic, not meaning that I wrote it small, but just meaning that we're looking at the behavior of individual molecules to build this formula. So 2 different formulas for bond energy. But it's not like we're talking about 2 different types of energy. These are just 2 different formulas for the same thing. And if they're 2 different formulas for the same thing, what can we do with these 2 formulas?
Set them equal to each other?
Yeah, we can set these equal to each other. And by doing so, we can get more information about what's actually going on. Later, we're going to be doing the same thing with thermal energy as well. You're building a formula for it macroscopically, the MC delta T as usual, and also building a formula for it microscopically by looking at the individual behavior of molecules, and then setting those formulas equal to each other to get even more information. But let's try that here. We should be able to set these formulas equal to each other. The macroscopic formula for bond energy better equal the microscopic formula involving behavior of the individual molecules. So we can set those equal to each other, and we can simplify this further as well. What shows up on both sides of the equation here?
The moles.
Yeah, number of moles shows up on both sides. So we could divide both sides by n, little n, number of moles. And also we've got a negative sign on both sides. So I'm going to divide both sides by negative n. That way, number of moles cancels out, the negative cancels out, and we're left with, what's all that's left on the left side of the equation? Everything cancels out except for
H mole is equal to the number of neighbors divided by 2 times the Avogadro number times epsilon.
Yeah. And of course, Avogadro's number and 2 are constants. So really the only things that differ from one substance to another that matter here are epsilon, the bond strength, and number of nearest neighbors per atom, the crystal structure. So that's really all that influences the delta H. The reason different substances have different values of delta H mole on the data table is because they have different bond strengths and or different atomic structure. So if you know these 2 things, if you know the structure and can count up the number of nearest neighbors per particle, and you know the bond strength of just a single pair of atoms, you can plug that into this formula and calculate or predict what delta H mole should be for that substance. And that goes in the other direction also. If you know delta H mole, because you can calculate this in a laboratory setting just by doing experiments on how much energy it takes to vaporize the substance. So if you know delta H from laboratory experiments, and you know the number of nearest neighbors because you know the crystal structure, you can calculate epsilon. You can figure out what's the bond strength between a single pair of atoms. So this is a very convenient and useful connection between what's going on macroscopically that you can directly measure and what's going on microscopically that's too small to measure, but that we can infer from other information. And this is really one of the biggest pieces of evidence in favor of atomic theory in the first place. The very idea of matter is made up of tiny particles called atoms was really kind of in doubt until 120, 130 years ago. And this idea that we can link the predictions made by the theory that matter is made of atoms versus actual concrete observable experiments that you can perform in a laboratory, this connection is one of the biggest pieces of evidence we have that yes, matter really is made up of tiny particles called atoms. Any other questions on that so far? Or any other questions on this bond energy stuff in general? All right, then let's try applying the same approach to thermal energy as well. See if we can figure out a connection between behavior of the molecules and temperature of the whole object. At the very, very, very small level, if we're talking about individual molecules, let's just say, for simplicity, let's assume we've got a monoatomic solid. So we've just got a whole bunch of bonded particles. And for purposes of bond energy, we're basically treating those particles as if they're at rest. But they're not really at rest. What are they doing?
Vibrating.
Yeah, these particles, even though they're bonded, they're all vibrating. They're on average staying in about the same place, but they are wiggling around, oscillating back and forth, centered at that equilibrium. And that means that in addition to just having the negative epsilon worth of bond energy, they've also got their own kinetic and potential energy. Kinetic energy because they're wiggling, potential energy because they're not always at equilibrium. They're moving back and forth around equilibrium. They're interacting with their neighbors. In fact, because of the shape of the Lennard-Jones potential graph at the low end, you can basically treat these as if they're connected by tiny invisible springs. If you just imagine these as if they're connected by tiny invisible springs and all wiggling around, you get a pretty good picture of what's going on here. And of course, there are no actual tiny physical springs here. It's just a metaphor for the forces between the atoms, the attraction and repulsion, but the behavior is almost identical. So in that situation, we've got kinetic energy and potential energy. And let's say macroscopically you apply some heat to the system. You just take this solid, you apply some heat, but not enough to melt it. That means macroscopically, what would you observe? You add some heat, and what would you expect to happen?
An increase in kinetic energy.
Kinetic energy of what? Is the object itself now moving faster?
Oh no, the atoms.
Yeah,
Molecules.
individual atoms gain kinetic energy. They're going to be wiggling faster. So if you add heat, microscopically, we would expect the atoms to move faster. In other words, an increase in the atomic kinetic energy on average. And I say on average because it doesn't necessarily mean they're all moving at the same speed. Maybe some of them are a little faster, some of them are a little slower, but on average, the kinetic energy per atom has increased. And also, if we go back to the Lennard-Jones potential graph, if you're at a low energy and you raise it to a higher energy, you've not only increased the speed at which they can move. What else changes about the kinetic energy graph when we raise E total?
How far away they get from equilibrium?
Yeah, we're changing how far they can get from equilibrium. Because when we were looking for R min and R max, we looked at the intersections. So in the low energy situation, we've got R min and R max, and the particles are going to move with a kinetic energy graph like this. They can get this far apart and this close together. But if we increase the energy, we again look for the intersections R max has moved outwards a little bit. R min has moved inwards a little bit. Our new kinetic energy graph is not only higher, representing a faster maximum speed, but it's also gotten wider. The particles can get further apart at R max and closer together at R min. So we've not only increased kinetic energy on average by allowing the atoms to move faster, we've also increased the average potential energy. The atoms can get closer together and further apart. They've got a wider range of motion. So the average potential energy has increased as well. So microscopically, the energy we've added as heat goes into raising the average kinetic energy and average potential energy of the individual molecules. But macroscopically, this is not what you directly observe. You don't see the individual molecules moving faster or getting closer and further. What would you be able to measure about the whole object?
The temperature?
Yeah, the temperature. Macroscopically, you add heat to the object and you notice that it gets hotter. The temperature has increased. So macroscopically, in the macroscopic viewpoint, the big picture, the temperature of the whole object has increased. And we could describe that as the thermal energy increasing. But these are not different phenomena. These are just two ways of describing the same thing. It's not like the temperature gets hotter and separately the atoms are moving faster and getting closer and further together. The temperature getting hotter is atoms moving faster and atoms getting closer and further. These are the same thing, just described in different ways. When we say the temperature is rising, what's physically happening is the molecules are moving faster and getting closer together and further apart. It's just two different ways of describing or measuring or talking about the same phenomena. Any questions on that so far? So when we look at these individual atoms or molecules on the microscopic level, we're going to be talking about this as kinetic energy and potential energy of the individual particles. But keep in mind that all of that is really the thermal energy of the whole object. We're just breaking it down into small pieces. And those pieces are what we call modes. Or in some textbooks, they're called degrees of freedom. Just two different terms for the same idea. 7 series usually calls them modes, 9 series usually calls them degrees of freedom, but same thing. The main idea is that a mode or a degree of freedom is a way for a particle to have energy. Or specifically, we're going to say an independent way for a particle to have energy. And when we say independent here, that's really a mathematical thing, a term from linear algebra. Independent in this context can basically be interpreted as perpendicular. Like the atoms can have kinetic energy, but they can have kinetic energy through moving in, how many different directions could they move in? 3. I mean, directions might not really be the right word here. They could move in many different directions, but we're only in a 3-dimensional universe, right? The atoms can be moving along the x-axis, they can be moving along the y-axis, which is perpendicular to that, and they can be moving along the z-axis, which is perpendicular to both the x-axis and y-axis. So we've got 3 perpendicular sets of directions they could move in. If it's moving diagonally, we could just treat that as a combination of x, y, and z directions. So we really only need to think of this in terms of 3 directions and combinations thereof. So that's what we mean by independent. The x-axis is independent from the y-axis, which is independent from the z-axis. There are 3 independent directions or dimensions. So because of that, we would say that the atoms have 3 different ways of having kinetic energy. You could have kinetic energy because you're moving in the x direction, kinetic energy because you're moving in the y direction, kinetic energy because you're moving in the z direction. So we would say that that's 3 kinetic energy modes. Or sometimes we call these translational modes. Translational because we're talking about translational kinetic energy, not rotational kinetic energy. So 3 translational modes, which count as kinetic energy. And also they can interact with their neighbors. So they're going to have potential energy. And in how many different dimensions can each particle interact with its neighbors? How many dimensions do we live in?
3.
Yeah, we're still in a 3-dimensional universe. Each atom has neighbors in 3 dimensions. It can interact with its neighbors to the left and right. It can interact with its neighbors in front and behind, and it can interact with its neighbors above and below. And again, of course, you could have diagonals, but we would treat the diagonals as just some combination of the x direction and y direction and z direction. So because we live in a 3-dimensional universe, we're going to say there are 3, and the name of this differs from situation to situation or textbook to textbook or even instructor to instructor. I usually call these vibrational modes, in the sense that the atoms are vibrating back and forth, and specifically external vibrational modes. Internal vibrational modes would be vibration inside a molecule. Like if you've got, let's say you've got an oxygen molecule, 2 oxygen atoms, those 2 atoms in the molecule could be vibrating back and forth along the molecular bond. That's not what we're talking about here. We're not talking about internal vibration. We're talking about external vibration, an atom or molecule interacting with other molecules nearby. But those definitely count as potential energy. Or sometimes we would just call this 3 potential energy modes. The important thing is there are 3 of them because we're in a 3-dimensional universe. And these are really the only relevant ways the atoms can have energy here. The atoms can move, the atoms can interact, and that's it. So we would say that each atom has 6 modes, 6 ways to have energy. And then in this case, if we want to know the total number of modes, we would just multiply that 6 times the number of atoms. We don't need to worry about double counting here because we're not talking about bonds. We're just talking about how many ways this atom can have energy and how many ways this atom can have energy and so on. So that means if there are some number of moles, we just multiply 6 times number of moles times Avogadro's number. As the total number of moles. Sorry, total number of modes in the whole substance. The total number of ways the entire sample can have energy. Any questions on that so far? And then to find the actual amount of energy involved, we have to take the total number of modes and multiply it by what? What are these modes storing? Each mode is just a way to have what?
It's just a way to have energy, right?
Right. So if this is how many ways the system can have energy, and specifically we're talking about thermal energy, we're just breaking it down into kinetic and potential energy of the atoms. But if we can figure out how much energy each mode has, we can just multiply that by the number of modes total, and that'll tell us the total thermal energy of the entire system. And this is where we get into an idea from statistics called the Equipartition theorem. And this has to do with how the energy is split up. If you just add a bunch of heat to this, that heat gets distributed to all the modes that are possible. The all 6 times moles times Avogadro's number moles or modes. But how does it get distributed? How would you expect the heat you add to get distributed to all these modes? Like, would we expect some modes to have more or some modes to have less or all about the same or what? Should be all the same. We expect the energy we add to the system to be evenly distributed amongst all the modes, but only under certain circumstances. Why would we expect all the energy to be evenly distributed? Why wouldn't some molecules have more energy and some molecules have less energy? Or would that even be possible? Like, can you have a situation where, like, let's say you've got a room full of air. Let's say these molecules have high energy and these molecules have lower energy. If that were the case, how would you notice? How would you notice that these molecules are high energy and these ones are lower energy?
It'd be hotter, right?
In the region where the molecules are higher energy per molecule, or rather higher energy per mode, the temperature is higher. But if the temperature is uniform everywhere, if we're at thermal equilibrium, same temperature everywhere, then we would expect all the modes to have the same amount of energy. In fact, this is really what temperature means. When we say the temperature is the same everywhere, we're really saying all the modes have the same amount of energy per mode. So the equipartition theorem is just saying if everything's at the same temperature, thermal equilibrium, then all the modes have the same energy on average. And again, I'm saying on average because it doesn't have to be the same all the time. Maybe at this instance, this atom has a little more energy and this atom has a little less energy, but it's going to average out. So if a system is at thermal equilibrium, all the same temperature, then we would assume that the thermal energy is evenly distributed, evenly divided amongst all the available modes. And we say all available modes because there may be circumstances where some modes are not active. Some modes are, we usually use the term frozen out. Like if the molecules are unable to do certain types of motion, then those modes would not be available. But we assume that the energy that's present, the thermal energy that the system has, is evenly distributed to all the modes that are possible. And that means that if the temperature is the same, they all have the same energy per mode, no matter what type of atom it is. If you've got like, and also no matter where they are, if you've got, let's say, a water molecule here and an air molecule 1,000 miles away, if they're at the same temperature, then they have the same energy per mode, no matter what type of molecule they are, no matter what state they're in, no matter where they are. Same temperature means same energy per mode, no matter what. Because that's really what temperature is. Temperature is the energy per mode, just written in different units. And that means that we can build a formula for energy per mode. Energy per mode, like the energy that one translational mode has, or the energy that one vibrational mode has, should depend only on temperature. Temperature is the only thing that influences the energy per mode. And it should be proportional, like 3 times as much temperature means 3 times as much energy per mode. So we should expect energy per mode to just be some constant times the temperature. And it turns out that constant is half of another constant called Boltzmann's constant, Kb. Boltzmann's constant. So we can use this as a formula for the energy in one mode. Energy per mode is half of Boltzmann's constant times the temperature. And since this is not a delta temperature, it's the actual temperature right now, that's got to be in kelvins. But you can use this to calculate the energy per atom, for instance. We know there's 6 modes per atom here. We know the energy per mode is 1/2 kb times the temperature. So how would you find the energy per atom?
You do 6 times the energy per mode.
Yeah, energy in one atom, or sorry, modes per atom, times the energy in one mode. 6 over 2 is 3, so we just get 3 times Boltzmann's constant times the temperature. So you can predict the energy in one atom in solid form. Or if you wanted to know just the kinetic energy, maybe you were trying to figure out how fast the atom's going on average. To get just the kinetic energy, how many modes would you use? 6 was the total number of modes per atom. That a single atom in a monoatomic solid has 3 translational modes because it can move in 3 dimensions, and 3 vibrational modes because it can interact with its neighbors in 3 dimensions, for a total of 6 modes per atom. Then each one of those modes has exactly kV/2 times temperature energy on average. So we multiply those together, number of modes per atom times energy per mode, and we get the energy per atom. But suppose we were trying to figure out how fast a molecule was moving. What would be the only modes we care about if we're just looking at how fast is it moving?
Translational modes.
Yeah. And the atom has just 3 translational modes. So the kinetic energy of one atom, translational kinetic energy, would be 3 times 1/2 kBT. And note that that also only depends on the temperature. If you've got 2 molecules that are at the same temperature, they will have the same kinetic energy. Doesn't matter what phase they're in, doesn't matter what kind of molecule. If they're at the same temperature, they'll be the same kinetic energy per atom. Of course, that doesn't necessarily mean same speed, because kinetic energy is about not only speed, but also what else? What other variable shows up in the formula for kinetic energy?
Mass.
Mass. So same temperature means all the atoms are all the particles are going at the same kinetic energy, but that might not mean same speed because they might have different masses. So you need to consider the mass as well. But 2 molecules with the same temperature will be going at the same kinetic energy on average. Any other questions on that? All right, so go through the questions in your FNTs. I think this idea of modes should clear up a lot of the questions there. Most of the questions on the FNT there should be designed to get you thinking about number of modes and how that influences energy. And then next time we'll look into how we can apply that to the macroscopic viewpoint of thermal energy and the idea of heat capacity as well. So feel free to email me if you have any other questions, and I will see you next time.
Thank you.
You're welcome.